Today, we're going to talk about one of the most important breakthroughs in the entire history of AI. And what's wild is, it wasn't some crazy complex algorithm or a giant new data set. Nope. It was a single, shockingly simple idea that finally allowed AI to get deeper and a whole lot smarter. All right, let's get into it. So, you got to appreciate the paradox that was driving researchers completely nuts. For years, you'd think the logic would be simple, right? More layers in a neural network means more power, more ability to learn complex stuff. But in the real world, the exact opposite was happening. After a certain point, when you added more layers, the network actually got worse. It was this incredibly frustrating wall that just seemed to defy all logic. And that wall, well, it had a name: the vanishing gradient problem. This was the fundamental barrier, kind of the main villain of our story, that was holding back the entire field of deep learning. Okay, so think of it like this. Imagine you're playing a game of telephone. The first person whispers a message, the next person tries to repeat it, and so on down the line. You know what happens, right? By the time it gets to the last person, the message is either totally garbled or it's just gone. That is exactly what was happening inside these deep neural networks. The message was the learning signal, the gradient. And with every single layer it passed through, it just got weaker and weaker. And you can really see the problem right here. In a shallow network, with just a few layers, that message gets through just fine. The early layers learn, the later layers learn, the whole system gets better. But in a deep network, that signal basically flatlines. The layers way back at the beginning get zero useful feedback, so they just stop learning completely. So how in the world do you fix a problem like that? Well, it turns out the answer wasn't more complexity, it was this incredibly elegant shortcut. So let's meet the hero of our story, the skip connection. First, let's look at the old way, the traditional path. You've got an input, we'll just call it X, and it goes into a block of layers. These layers do a whole bunch of complicated work on it. We can just represent all that complex stuff as a function f of x. Think of that as the long, winding road with lots of turns. And then, this happened. This is honestly one of the most important equations in modern AI. The output isn't just the result of all that complex work, f of x. You also just add the original input, x, right back in at the end. That's it. That is the entire trick. It is just breathtakingly simple when you think about it. And this is what we call the skip connection. It basically acts like an information highway, an express lane. While that main path is doing all the hard work, learning all the complicated features, this highway makes sure that the original signal, that original message, always has a clean, direct path through the network. The learning signal can just flow and it never, ever gets lost. Okay, so the theory was brilliant, but did it actually work in practice? Well, let's get to the test that proved its power. A model called ResNet, short for residual network, taking on a really tough computer vision challenge called CIFAR-10. Now, CIFAR-10 was no joke. We're not talking about simple black and white handwritten digits here. This was a real test with tiny 32 by 32 pixel color images of stuff like airplanes, cars, birds, and horses. The model had to deal with different angles, weird lighting, cluttered backgrounds. It was a huge jump in difficulty. And this was the machine they built to conquer it. ResNet 18. You can see the basic blueprint right here. It kicks off with a standard convolution layer to process the image, then it flows through 4 main stages built from these new residual blocks, and then finally a classifier at the very end makes the call. So the image starts at 32 by 32 pixels. As it goes deeper and deeper through those residual layers, the network is constantly shrinking the image dimensions from 32 by 32 down to 16, then 8, all the way down to 4 by 4. And it's learning more and more abstract features every step of the way. All right, so the stage is set. We've got the revolutionary architecture facing this tough challenge. How did it do? Let's look at the results that really did change everything. And here it is. This is the crucial point. The old standard Linnet 5, with its 5 layers, it kind of topped out around 60% accuracy on CIFAR-10. But ResNet 18, a much deeper 18-layer network, didn't get dumber. It got way smarter. It just blew past the old benchmark.
hitting over 75% accuracy. The wall was broken.
In the specific training run that we're looking at from our source material, the final test accuracy was a solid 76.8%. And look, this wasn't just a tiny improvement, it was a massive leap forward. It proved that with the right architecture, deep could finally actually mean better. And ResNet didn't stop at 18 layers, not even close. That same simple principle, that same skip connection, allowed researchers to build and successfully train networks with a staggering 152 layers, and even more. The floodgates were officially open. This chart really puts the scale of the revolution into perspective. LeanAt 5 had about 62,000 parameters to learn with. ResNet 18, it had almost 12 million. That's nearly 200 times the capacity. And because of those skip connections, all of that extra capacity could actually be used to learn effectively. It created a completely new baseline for what was possible.
So, what's the big takeaway here? Well, ResNet teaches us a really powerful lesson. Sometimes the most profound breakthroughs don't come from more brute force, but from a moment of just elegant simplicity. It really makes you wonder, if one simple plus sign could fundamentally change the course of AI, what's the next game-changing shortcut?